So today we're going to learn how to do Lewis structures and review this because you learned it in pre-AP chemistry. Really? So this is day 2 I've talked and you haven't stopped. You're on a roll with me. Maybe if you turn your feet around, put them forward, you won't be as tempted. And I'm picking on you because you're the one with the back turned to me. Everyone else around you is just as guilty. I'm aware of that. It's your bad as well. Yeah, you have his back. I'm glad. So you both can go out in the hall together and sit while I talk? No? No? Okay. Lewis structures. Lewis structures are those dot structures that you drew where you had the bonds as lines and all the dots and pairs around the outside and all that stuff. Remember those? Okay. Those are actually representations of only covalent compounds. We cannot draw Lewis structures for ionics. Why not? Yeah, the covalents actually are sharing these electrons. Okay, the ionics, they're just a bunch of oppositely charged things sticking to each other. So they don't have this type of shape that we're going to be looking at when we get into Vesper and stuff next week. Let's see if we remember how to do it. At Westlake, we teach the needed available shared method. So whatever Chem 1 class you did, it doesn't really matter. You learned it this way. If you took General Chem, they called it NASL. If you took Pre-AP, they just called it needed available shared. And let's review what that meant. You ended up looking at the periodic table for 3 numbers. N was the sum of all the elements in the compound and how many electrons they each individually needed to have that complete octet. For the most part, we're dealing with octets. There are some exceptions. Pretty much everything needs 8. So you're going to say everything needs 8 except for a couple of them. Hydrogen and helium need 2. Correct. So those are a couple of exceptions. So when we have hydrogen in our covalent compounds, we're just going to put 2 for the N instead of 8. There's also beryllium and boron. Those are electron deficient. We're not getting into reasons behind the deficiency, but who remembers beryllium needs 4 and boron needs 6. So just remember, one's 4 and one's 6, and they go in order across the periodic table. All right? So when we see those, we put 4 or 6 in for the needed. A is how many of these things actually have in terms of valence electrons. You can look at the electron configuration and look at the valence, but there's also a shortcut by looking at the Roman numeral on the periodic table above the actual column. So for instance, oxygen is 6 valence electrons. I don't ever want you to forget, though, where that 6 is coming from. Remember, oxygen has an electron configuration of 1s2, 2s2, 2p4. It's the 2s2, 2p4 that's adding up to those 6 valence, okay? So don't ever forget what those valence or those Roman numerals actually represent. So we total up how many they have as valence electrons, how many they actually have. I say A is actually. Then you subtract them, and you get how many you share. So this is how many they need, how many they actually have, and how many they share. So if you divide the number of electrons they share by 2, that gives you the number of what? Bonds. And so this dictates how many bonds has to be in your picture. At that point, you use up all those in bonds, and then how many available you have left over you will place in other places on the picture. And once I review this, you'll be like, oh yeah, I remember now how to do this. This is just restating what I said about hydrogen having the need for only 2 electrons in its outer shell. Most things need 8. We can draw bonds that are single. So this is a sharing of 2 electrons. We can draw double bonds, so that's sharing 4 electrons. We can also draw triple bonds, and that's sharing 6 electrons. And this irritates me because these pictures aren't complete. One thing you'll learn about me is mainly, I think I've turned into an electron witch since I started teaching organic, because all of organic is around the movement of those electrons. So those pairs that you just place randomly are just as, if not more important than the pairs and the bonds. So I expect to see them. I don't want to question, oh, did they just drop their pencil there and make a little mark, or is that an actual dot? I want to see these dots, okay? So please always have your dots in your pictures. So we're going to draw Lewis structure for these. We're starting out, baby, easy. Probably don't need the needed available shared for this. You definitely don't, but I just want to practice the procedure. So how many does each hydrogen need to be full? 2. So that's a total of, there's 2 of them, so that's 4. How many do we have available with 2 hydrogens? 1 each, so that's 2. So we're going to share 2. That's putting 1 bond. Okay. Of the 2 that I shared, I've used up all the available, so I'm done. You'll see in some textbooks this. They will take it on the AP, but I highly discourage it because it leaves room for more mistakes if they're not very clear. So I encourage you to draw your bonds as lines, not dots. Okay? All right, F2. Needed, available, shared. How many do we need? 8 plus 8 is 16. How many do we actually have? 7 plus 7 is 14. We're going to share 2. How many bonds is that? 1 bond. So of the 14 available, we've used up 2. That leaves us 12 to pass around. We place them in pairs in order to give everything their full outer shell. So we have 12 left. 2, 4, 6, 8, 10, 12. Okay? All right, HF. I'll do it in a different color over here. We know H and S. These are easy. How many do we need? 8 plus 2, right? So 10. We actually have 7 plus 1 is 8, so we're going to share 2. Oh. So how many do you have left to pass around? 6. 2, 4, 6. And there it is. Does this have a dipole moment? All right. No, only if you're asked. I just got the urge to show you a dipole moment there for absolutely no reason. Okay. Now we're getting into some more complex molecules. When you're doing these, there's a general rule of thumb that the more electronegative element goes in the middle, and that's going to be the case for the most part, except for your carbon-containing compounds. Carbon loves to make 4 bonds, so when it has a chance to get in the middle and do that, it's going to. And that's going to be less electronegative than a lot of the things that attach to it. But for the most part, we're looking, I don't want to say we're looking for symmetry, but since we have 3 N's, 3 H's and 1 N in this example, the N is going to be the central atom. H can't be the central atom anyway because it only can make 1 bond and it's full, so it has to be an external atom. You always have a central atom. Don't start taking stuff and making lines of things unless, of course, you're dealing with an organic compound. Otherwise, pick the 1 atom that's going to go in the center. So I'm not going to really beat you up yet about how you draw these as far as shape. If you just spread those evenly around the center, you can. Me knowing what shape this is, I'm going to start drawing the shapes correctly in order to help you get used to that. So, needed, available, shared. How many do we need? 8 plus 3 times 2, right? 14. 14. How many do we actually have? 5 plus 3 is 8, so we're going to share 6, right? So those are the 3 bonds. That's 6. How many do we have left? How many lone pairs? How many lone pairs? 1 lone pair. We're going to place those 2 electrons there. I happen to know, because I know Vesper, that lone pair repels those bonded pairs. So rather than those H's just happily being spread out, they're repelled down, and so this looks like a little pyramid. Okay? So once you start learning the shapes, it'll be good for you to be drawing them appropriately because that helps you with polarity. That helps you do reactions when they ask you how things will make other things dissolve, all that sort of stuff. Knowing the shape helps. All right, CO2 is going to open a little bucket of worms that we're going to address more on Monday. But let's go ahead. How do you think it looks? No, not the bonding, just the arrangement. Yeah, so we'll do that. And then needed, available, shared. Now, I know oxygen's more electronegative. However, carbon, again, when it has that center opportunity, is going to do it. So 8 times 3 is 24. We have 6 plus 6 plus 4 is 16, so we're going to share 8 electrons. How many bonds is that? 4. You're inclined to place them a certain way because you kind of been taught that, but there's actually 3 different what we call resonance structures to this. And we're going to hit this a lot harder on Monday, but what would be the first way you would like to place these? 2 and 2. So that leaves me 8 electrons to place. Where am I going to put them? On the oxygens, 2, 4, 6, and 8. So that's correct, and that is your most stable form of CO2. Have you ever wondered why, other than the fact it was symmetrical? Because symmetry is not always the case. Well, we're going to learn that on Monday. We're going to talk about formal charge Monday. So next, we're going to look at, what's another possibility? 3 and 1. So all our electrons, well, most of them go here, and we only have a pair there. And what's the other resonance structure? The other 3. Now, a lot of you're probably thinking in your head, well, those are the same. If you flip it, they're not the same. Because when you get to organic chemistry, you're going to learn how these electrons can move in the actual structures and do all these different kinds of things. So within one existing molecule, this guy right here, we can have electrons switching around doing that in 3 different fashions. So we end up having 3 different molecules. Okay? Because this is the most stable, that's going to be in existence majority of the time. But again, that's a Monday topic. We'll talk about that on Monday. All right, so, and I can't move this. All right, the last one is carbon tetrachloride. So carbon's in the center. We have our chloride, chlorines on the outside. Needed, available, shared. How many do we need? 40. 8 times 5 is 40. We have 7 times 4 is 28 plus 4 is 32. So we're going to share 8. How many bonds is that? 4 bonds. 1, 2, 3, 4. Done. If you see a number here, that's how many electrons have to be in bonds. Don't be trying to get creative. You have to do it that way. Now that leaves us how many to pass around? Now we used up 8. We have 24 electrons still to place. So we're going to place them in pairs around the periphery. 2, 4, 6, 8, 10, 12, 14, 16, 20, 22, 24. Wait, I can't count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I skipped 18, I think. I don't know. I skipped something. All right. Good? Yes, Miles. That's fine. This is actually not flat in space. It's not a square. It's not square planar. Who remembers the shape of things with 4? We talked about that a little bit yesterday. Yeah, it's tetrahedral. So those things in 3-dimensional space are actually surrounding the carbon. We'll hit that next week. All right, let's talk about those exceptions again. Boron, we know, only needs 6 to be full. We talked about beryllium. It only needs 4. You don't do those problems any differently other than instead of getting 8 in the needed, in the N slot, you use 4 and 6. That's the only thing different with those. However, we run into situations where we have some of these central atoms. What can you tell me about them? How many does AS have around it here? 10, and this one has 10 as well. So I thought 8 was the octet. Well, some elements can expand their octet. Which elements can do this? Well, let's talk about original valence electrons and the whole idea of 8. We say 8 was valence electrons because it came from which orbitals? Which orbitals can we get? S and P. So 3 P's and 1 S orbital give you 8 electron possibilities, right? So if I'm going to expand my octet, where am I getting those electrons from? Which orbitals? There's got to be other orbitals we're accessing. D's. So we're going to start to access the D orbitals. However, D's aren't on every level. What's the first sublevel of D's? What's the number? 3. So any element on level 3, or it's actually, yeah, level 3 or beyond, can actually expand this octet. No, that's a good question. No, actually, even the S's and the P's on their level 3 can access it as well. So starting with sodium, magnesium, aluminum, phosphorus and sulfur very commonly expand their octet. So anything on level 3 or beyond can do this. I don't know if you guys remember the last unit, you had a couple questions that I asked you to do for practice. One of the questions was, how come we can, for P can do PF3 and PF5, but N can only do NF3. You remember that one? And that was the reason. This has no d orbitals available on the energy level 2 in order to expand that octet. Phosphorus, being a third energy level element, can do that. So the question you're probably asking is, how am I going to remember this? Is it always going to expand? When does it expand? The beauty about needed, available, shared, when you do it, if it's an exception, needed, available, shared is not going to work. You're going to see something, you know, I can't do it that way, and that's your clue that it's an exception. So let's go ahead and look at a couple of those. BF3 isn't really going to be any different. Let's go ahead and give it a try. Needed, available, shared. The only thing we change is boron needs 6. So F needs 8. 8 times 3 is 24 plus 6 is 30. 7 times 3 is 21 plus 3 is 24, so we're going to share 6 electrons. So the 6 electrons are here. How many do we have left to pass around? 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That one was easy. So the B and the BE, no big deal. Where we need to watch ourselves is on the exceptions. Now, from my experience and just knowing, I know that's an exception. Maybe you can kind of tell. Can anyone see why we would know this is an exception without even starting it? There's 5 things attached. But let's say you're in a cloud when you're taking your test and you don't remember that. You don't even look. You're like, I'm doing needed, available, shared. I want you to see what happens when you do needed, available, shared on an expanded octet. Needed is 6 times 8 is 48. Isn't it weird how I know 6 times 8 is 48 better than I know 8 times 6 because of the rhyming thing? Okay. Anyway, just thought I'd share that with you, and I'm glad that went over so well. 7 times 5 is 35 plus 5 is 40. So we're going to share 8. That's 4 bonds, right? If you set this up, can you do this picture with 4 bonds? That is your clue. Uh-oh. Oh-oh. I should do uh-oh. So that means we have to follow the following steps. And they're not hard. Don't freak out. When you see an exception, all you do is you take your available electrons. That's how many you have, right? And that's the number you look at. Then you're going to bond everything singly to the central atom. And you need to be counting while you're doing that because that's 2 electrons per bond. Then you're going to fill all the outer elements or atoms with electrons until they're full. And then if you have any left over, you put them in place remaining on central atom in pairs. And they all have to add up to that available number. So here we have 40. So just watch what I do. 2, 4, 6, 8, 10. Now I start filling up all those CLs on the outside. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. That's it. Everything's full, right? So I'm done with that one. Yes? So, if there's only 40, are you really taking the needed? Or do you have to... No, you never take the needed. The needed is trying to figure out how many everything would need. If all those were by themselves, how many total you would need. It doesn't take into account stuff that they're sharing. That's why you do the subtraction. No, I counted the 10. I only put 30 on the outside. I counted 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. There should only be 40 electrons in your picture. The A is the number of electrons you have in your picture, no more. That's all that you have. That's all that's available. So I'm going to change this little guy up because I don't like him. It's too easy. I want to make this a little bit more of a different one. So we're going to do xenon tetrafluoride. For xenon tetrafluoride, I know that's an exception. Why would I know? There's only 4 things attached. How do I know that's an exception? Any ideas? It's a noble gas. Xenon already has 8, so bonding is going to, in order to bond, it's going to have to expand. But again, let's pretend you don't recognize that, and you need it available shared. Xenon, we're hoping to have 4 bonds here, right? So needed, how many do we need? 4 times, or 5 times 8 is 40. How many do we actually have? 7 times 4 is 28 plus 8 is 36. So we're sharing, holy crap, how many bonds is that? Uh-oh, I can't do that. So this has to be an exception. So again, for an exception, I take my available. That's the number I use. And I'm going to now bond the center, 2, 4, 6, 8. Now fill the periphery. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've got 4 more electrons. What do I do with them? Place them as pairs on the central atom. Do not do this business. I will kill you. You place them in pairs on the central atom. Okay? Because what happens is, we're going to learn on Tuesday how these lone pairs affect the bonded pairs, and we get different shapes, different polarities, different bond angles, all that kind of thing. Okay? All right, we're almost done. Okay, I'm going to change this one to... All right, let's look at number 16. It says, write the Lewis structure for C2H4. That's an organic molecule. That's cool about these CH organics. You really don't need to do needed available shared. If you decide you want to, that's fine. But all you need to know is each hydrogen will bond 1 bond. How many bonds does carbon always make? 4. So you're going to fill this stuff up with bonds until carbon has 4 bonds and hydrogens have 1 bond. And they're carbon chains. So if we have 2 carbons, we're going to first hook those up, right? Now, the hydrogens are going to be placed symmetrically. And so how many are we going to put on each carbon? 2. Now, we're not done here because carbon only has 3 bonds. So what do we need to do? Double it up. And that's it. You never really have to do needed available shared. However, if you do decide to do it, you'll get the correct number of 6 bonds that you have to place in the picture. So it won't hurt you to do it, but it's just such a time saver for these organics just to draw them out. All right? Okay. HCN, just a different one for another level of practice. Again, C likes to do its thing in the middle, given the opportunity. Needed, how many? Is that right? 16 plus 2 is 18. Available? 10, good. So we're going to share 8. How many bonds is that? 4. How are we going to place them? There can only be 1 there, right? So we're going to put the 3 here. We still have 2 electrons that we shared 8 of them. We still have 2 to place. Where are we going to put them? We have to put them on the nitrogen. Carbon's full, hydrogen's full, nitrogen needed 2. Okay, the last thing I want to look at really quick is these charges. Okay, that does change the game a little bit, but it's not too big of a deal. When when something is charged, it's lost a valence electron or it's gained a valence electron. So it doesn't change how many nitrogen and hydrogen needs. It's just changing how many you actually have available. So for NH4, something, another ion, I don't know what, came and stole an electron from it. So that takes away 1 from the available. So when you have things that are charged, you add or subtract things from the available, not from the needed, from the available. So let's take a look at this. Needed, available, shared. How many do we need? Yeah, 2 times 4 is 8, plus 8 is 16. We actually have 5 and 4 is 9, and this is where you're going to know something's wrong. Let's say I forgot about the charge and just put 9 there. What would that give me here? An odd number of electrons, and I can't share 1 electron. Okay, I can't have an odd number of electrons. So I know this is wrong. That's because this is plus. So did I lose or gain an electron? I lost an electron, letting me share 8 now. So my nitrogen's in the middle. So I get 2, 4, 6, 8. And I used them all up, right? So I'm done. Technically, we're going to learn about formal charge and how else you can write it. But for now, when you have ions, you put them in brackets and you put a plus. That's just to help whoever's looking at the picture know that there's 1 less electron in there than there needs to be, or than there should be. Okay? So do you notice how this is a polyatomic ion that you've learned? All polyatomic ions will then form an ionic bond with something else electrostatically, but within itself, it is covalently bound. It's hanging on and sharing electrons. It's these covalent bonds in the polyatomic ions that will keep them from dissociating in water as well. Remember we talked about if I had ammonium nitrate, for instance. If I put that in water, what 2 ions do I get? Ammonium and nitrate. I'm not breaking up the integrity of the covalent bonding that's within the ions. So every polyatomic in the whole wide world, you can draw a Lewis structure for. All right, last one. I minus 3. What's the central atom here? I3 minus, sorry. I. Okay, needed. 8 times 3 is 24. And how many do I actually have? 7 times 3 is 21. Plus 1 is 20. Huh? I'm going to share those with 1 bond. So what is it? It's an exception. So I should take those 22 electrons now. I have to include that extra one and do what we learned earlier. So I'm going to bond everything singly. 2, 4, go to the outside. 6, 8, 10, 12, 14, 16, 18, 20, 22. This is actually a linear molecule. These lone pairs are driving those bonded pairs crazy. They're like pushing them, repelling them down, repelling them up, and the bonds are like, ah! So the only way they can be far away from those lone pairs is to just be straight. So this is a linear molecule, and we're going to do a -1. We'll get to the shapes. Don't worry about it. I'm just giving you some preview information. So you guys are going to be capable of finishing your 4 homework problems, so you'll not have homework over the weekend. So go Shaps.